Hello, this is Mr. Henry, and welcome to lesson 4.11, Systems of Linear Equations. So the rest of this unit, we got 4.11, 12, 13, 14. So the next four lessons here are all going to be devoted to systems of equations. So what we're going to be doing is looking at two equations per problem and trying to find out what values make both equations true. In this lesson, the essential question says we're going to be solving by graphing. Soon, we'll be solving by algebra. And you're going to get a little reprieve from word problems for these first couple of lessons because the whole last lesson, 4.14, is devoted strictly to word problems. So every single one of those is going to be a word problem. Okay. So let's get to our warm-up. It is a type 1, and the question asks, what does it mean if we say that 3 is a solution to the equation 4x minus 6 equals 6? So what does it mean if we say 3 is a solution to that? Go ahead, pause the video, put down your answer. You move on to the vocabulary, hit play, and we'll move on. Vocabulary. We have two vocab words here. First one is a system of linear equations. So a system of linear equations consists of two or more. We're just going to see two equations, but it is possible to have more than two equations. So two or more linear equations with the same variables. And I have an example here of x plus 2y equals 7 and 2x minus 2y equals 5. So those two equations together in one problem makes a system of linear equations. And the solution of a system of linear equations is simply an ordered pair. So it's an x and y pair that satisfies each equation in the system. That means it's one pair of x and y. So one point on a coordinate grid, one xy coordinate, that is true in all of the equation. It makes all of them true. And that's what we're looking for. So the first thing we're going to do here, it asks us to find the solution to the system of equations. So I have two equations here. The first equation is this 3x minus 2y equals 5. And the second one is x plus 2y equals 7. And we want to find the solution. So we want to know what x and y coordinate, what point is there on the coordinate grid that would make both of these true? So there you go. I just want to make my dot a little bit bigger. So obviously, like this point out here, this won't work because that point doesn't even satisfy either equation. For an equation to be true, for the point to be true, it has to be like on the line. So right now, this point satisfies this equation. That point, wherever that point is a solution to this equation. And I can check that if you really wanted me to. So, just as proof, I'm going to imagine that's what, 1, 2, 3, 4. That's like 4.75. So with an x value of 4.75, 2y equals 5 should give me a y value of like 1, 2, 3, 4, maybe 4.5. So 3 times 4.75 is 14.25. Minus 2y equals 5. I'm now solving the equation for y, so I'm going to subtract this 14.25. Negative 2y equals, that looks like it's going to be a negative 9 something. So negative 9.25, and divide both sides by negative 2. And we have y equals 4.625, which is pretty much exactly what I said. So that point right there would now have the coordinates of 4.75, 4.625. That is true for this first equation, but it's not true for the second equation. If I would plug in an x value of 4.75, it's not going to work out on this equation because it's not on the line. So what we're trying to do is trying to find out where on this graph I could plug that point, or I could move that point so that it's true for both equations. And you might have figured it out right now. The answer is at the intersection point. Right there is the only place on the graph where both lines would have the exact same x and y coordinates. So that is the point we're going to check. We think that that is the solution. We think that is where the x and the y coordinates will be the same for both of them. So what would that coordinate be? 1, 2, 3, 3, 2. So if I plug in 3, 2 into both equations, hopefully both equations will be true. Let's check. 3 times 3 minus 2 times 2 hopefully equals 5. And 3 plus 2 times 2 equals 7. I'm plugging in the x coordinate for x, the y coordinate for y, and checking to see if that point is a solution to the system of equations. So 3 times 3 is 9, 2 times 2 is 4 equals 5, and yes, that is true. So this point here definitely works in my first equation. It is a solution because I got a true statement. Second equation, 3 plus 4 equals 7, and yes, 3 plus 4 does equal 7. So that point also works in the second system of equations. Moral of the story is, what you're supposed to get at this first problem, the solution to a system of equations, when graphed, is their intersection point. The point where the x and the y coordinates of both lines are the same. Right there, on this line, that's the point 3, 2. On this line, that's the point 3, 2. That is the same point in both of them, and it's always going to be true because it's on the line. It's on both lines. Letter B. Same deal. Now we're going to find the solution to the system of equations, and we're going to check our answer. So if you got it from the first problem, the solution to this equation would be, well, this is a solution to one equation. If I move the point over here, that's kind of a solution to the other equation, and the only place where there's a solution to both would be right there. So we think, well, no, that's the point 1, 1, 2, negative 3. So 1, negative 3. So that's the point we're going to check. Because that point is on both lines, you can see. And since it's on the line, it is a solution to that particular equation. And since it's on both lines, that point is a solution to both equations. So an x value of 1, a y value of negative 3. X value of 1, y value of negative 3. Okay, let's check. 1 minus negative 3. Well, minus a negative is just plus a positive. So that's 4 equals 4. Yep, that one worked out. So this first equation, it's definitely a point on there. The second equation, 4 times 1 is 4. And plus a negative 3 is just minus 3. 4 minus 3 is 1 equals 1. And yep, that one worked out as well. So that point makes both equations true. That point is a solution to both equations. And we have our answer. The solution to that system of equations is the point 1, negative 3. The solution to this system of equations was an x value of 3, a y value of 2, which is the point 3, 2. That is the solution to this problem. When x is 3 and y is 2, both of them are true. When x is 1 and y is negative 3, both equations are true. Okay, here is letter C. It says find the solution to the system of equations, which is the same thing we did in the previous two problems. So you have a graph of these two equations down here in blue is what they are. Go ahead and solve the system of equations, find the solution that satisfies both, and check your work. When you're ready to continue, hit play, and we'll go through it together. All right, so here we go. We're going to, well, the point appears to be this point right here, which has the coordinates of 3, 2. So that's what we're going to plug in. We're going to plug in an x coordinate of 3 and a y value of 2. And this side is pretty easy. 3 plus 2 is 5, so this side definitely checks out. Other equation, negative 2 times by 3 plus 2 equals negative 4. All right, so we're going to multiply, give us negative 6 plus 2 equals negative 4. And that simplifies to negative 4 equals negative 4. That works. So the solution to this system of equations is when you have an x value of 3 and a y value of 2, which is the point 3, 2. That is your solution. That's the point we found that satisfies both equations. Letter D here, little wordy problem, says Jasmine goes to the store and buys $30 worth of Skittles and chocolate bars. The chocolate bars are $2 a bag, and Skittles are $3 a bag. If she bought 5 more chocolate bars than bags of Skittles, how many of each did she buy? So this system of equations, or this problem, would be hard to solve without a system of equations. You could do some guess and check, and you could try, well, what if she buys 1 chocolate bar? What if she buys 2 chocolate bars? And just go through and do the math that way. But if you use a system of equation, it makes it easier. So what we have to do is, from this word problem, we have to pick out 2 statements that are true, that we know are true. So for example, the first one I have here for us, it says the total amount of money she spends is equal to the amount of money she spends on chocolate and the amount of money she spends on Skittles. Makes sense, right? So let's throw some numbers in that place. So this would be our verbal model. Let's get our equation. So how much money does she spend total? Well, $30. Okay. How much money does she spend for chocolate? Well, it doesn't say exactly. It doesn't say she spends $12 on chocolate. It says the chocolate bars are $2 each. So if the chocolate bars are $2 each, that means she would be spending $2 for each chocolate. I really don't want to put a C here and an S there because I like using the X and the Y. How about this? What if we just up top here we say X equals the number of chocolate, and then Y is the number of Skittles. So we can keep using the X and the Y that we're used to seeing. So 2X. So for every chocolate bar she buys, it's going to cost her $2. So if she bought, for example, 2 chocolate bars, 2 times 2 would be $4 worth. Makes sense. Okay. And plus the amount she spends on Skittles, and Skittles were $3 a bag, so 3 times, instead of using S for Skittles, we're using a Y here. Okay. So this statement is true. If she bought chocolate and Skittles and spent $30, we could graph this and see all the different combinations of Skittles and chocolate she could buy that would add up to the $30 that she spent total. The second part of the problem says if she bought 5 more chocolate bars than bags of Skittles, how many of each did she buy? That's where the second part of this problem comes in. So if she bought 5 more chocolate than Skittles, and here's my little verbal model that models a scenario. 5 more chocolate bars than Skittles. So if you take the number of Skittles and add 5, that would be how many chocolate? 5 more chocolate than Skittles. So this amount is now equal to that amount. So if you take the Skittles and add 5, that'd be the same number as the number of chocolate bars. So if we take this and make it into our equation, we said the number of Skittles was our y, the number of chocolate was our x. So what we have now is we have 2 equations, each with 2 variables. We can solve that system of equations the way we did in the previous problems. We could graph them. Now, being a nice guy, we haven't got there yet. I went ahead and I graphed them for us. So this is the equation of 30 equals 2x plus 3y. This was the scenario where she spent $30 and bought chocolate for $2 each and Skittles for $3 each. This equation, or this line, shows that the scenario where she bought 5 more chocolate bars than Skittles. So the number of Skittles, if you'd add 5, would now be equal to the number of chocolate bars. And here they are, both graphed on the same graph space. So what is the solution to both of these equations? Well, the solution appears to be this point right there. That is where both equations are true. That's where it's true the amount of money she spent, or it's true where this number and this number make this side true. And it's also true for this equation where the amount of money she spent total would be $30. So what is that point? That's the point 9, 1, 2, 3, 4. 9, 4. So we're predicting that if she spent 9 x's, what were the x? We wrote this down for a reason. X is chocolate. So she bought 9 chocolate bars and 4 bags of Skittles, then both of these would be true. She would have 5 more chocolate bars than Skittles. Look, 5 more chocolate bars than Skittles. But also the total amount of money she would spend would be $30. Well, let's check. So y plus 5 equals x. That one we kind of already verified, but we'll still do it. And 30 equals 2x plus 3y. So 4 plus 5 equals 9, and yes. So she definitely bought 5 more chocolate bars than Skittles. We can tell by even looking at our coordinates. And if you remember, just for yourself, x was chocolate and y was Skittles. Okay, this side. 30 equals 2x, so 2 times the number of chocolate, plus 3 times the number of Skittles. That's 18. That is 12. That gives us 30. So that's true as well. So based off this problem, Jasmine goes to the store and buys $30 worth of Skittles and chocolate bars. The chocolate bars are $2 each, and the Skittles are $3 a bag. If she bought 5 more chocolate bars than bags of Skittles, how many of each did she buy? She bought 9 chocolate bars and 4 bags of Skittles. And there's our proof. Okay, so this is a very common type of problem, or I say not very common. It's a common type of problem you're going to see later on. These are problems that involve you to do a little bit extra, a little bit beyond, because you have to start by coming up with your verbal models, your two different scenarios, the two true statements in the problem. Then you write your equations from it. Then you take your equations, and one method of solving is to graph. We're going to learn other methods of solving system equations over the next couple lessons, but the method we're looking at today is you could graph the system of equations, or a graph might be drawn for you. You find their intersection point, which is where both equations are true, and that intersection point is the solution to the system of equations. So, what is significant about the intersection point of both lines? Where the two lines intersect, what is significant about that? Go ahead, pause the video, answer the question. When you're ready to continue, hit play, and we'll answer this one together. Well, the significance of this intersection point, it's where both equations are true. It's where the solution of one equation and the solution of another equation are the same. Because every point along this line is a solution to the first equation. I'm just going to make up two equations. They're not actually going to intersect right there, whatever they are. So I'm going to say y equals negative 2x plus 3, and this will be y equals 3x minus 5, whatever. So they kind of have the same right picture-ish. So every point along this line, if I would pick this point right here, that point is a solution to this equation because that is an x and a y coordinate that make this true. And right there as well, and right there, and right there, and right there, and right there. This is the only point that is true for both of them, because that point right there in the middle is true for this bottom equation, and it's true for the top equation as well. That's why it's important. Now, example 2. What we have to do now is we're given a system of equations. You see them down below here. Here's our two equations. And we need to graph them. Now, pretty much the only way we've learned to graph so far is by using an XY table. There's nothing wrong with an XY table. The XY table works just fine. But it's not the quickest method. So I'm going to show you the graphing here a little bit. As we're solving this system of equations, we're going to learn them both together. So we know the system of equations is the solution is the intersection point. Well, in order to find that, we have to graph these two. So let's get to it. The method that most people would use when graphing an equation is they would use the slope-intercept form, which is this one. Y equals mx plus b, where m is your slope and b is the y-intercept. So, well, why would people use that one? Because it's the easiest. Because I don't need any other information. I don't need to do anything else to that problem. I can tell you exactly what that graph looks like. This graph has a y-intercept, and this is the first place you start. It has a y-intercept of -4. So this line crosses my y-axis at -4. -1, -2, -3, -4. I guarantee that is a point on this line. So I found my y-intercept. The second thing I would do is I'm going to move the way the slope tells me to move. Remember, that slope is the change in y over the change in x. So if that slope goes up 1 over 2, up 1 over 2, and repeat, up 1 over 2, up 1 over 2. You keep doing that all day long, these little stairs, up 1 over 2, up 1 over 2, up 1 over 2. This is my line. Actually, you can do the reverse. See, it's going to go down this way, down 1 over to the other way. This is my line. So this is the line of the equation y equals 1/2 x minus 4. Now, the other equation. This equation is not in slope-intercept form. Slope-intercept form is y equals. We don't have y equals. We could get it very easily. It's going to take one step. All we have to do is get rid of this x over here, and we would have y equals. So let's do that. Let's get rid of that x. So we're going to add x to both sides because he's a negative. Add x. Y equals x minus 7. You can't combine them because they're not like terms. And now we can graph. So we start with our intercept. Our intercept is -7. So 1, 2, 3, 4, 5, 6, 7. Right there is where this line crosses the y-axis because that is the y-intercept. And the slope here is the number in front of the x. Do you see it? How many x's are there? If your answer is 1, you're right. It is 1x. You go, wait. This is supposed to be like rise over run. How far you go up and how far you go sideways, but I just have a whole number. I don't have a fraction. And you're absolutely right. We don't have a fraction, and we want one. So all you do is you write the number 1 as a fraction, which is 1 over 1. That's still the number 1. It's just as a fraction now. So I'm going to go up 1 over 1. 1 over 1. Up 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 1. Ha 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 ha. That's where my 2 points intersected. Keep going. Up 1 over 1. Up 1 over 1. Down 1 over 1 the other way. And this is my line. Doot, 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 doot. So we have now graphed both equations using this slope-intercept form. And it's called sloped-intercept form because the equation has the slope of the line and the y-intercept of the line. We started, you have to find some place to start on your graph, and the starting place is on the y-axis. It's the y-intercept. So you put your point on the y-intercept, -7. -4. Once you have a starting point, then you move the way the slope tells you to move. The slope here was 1 over 2. So you go up 1 because it's positive, up 1 over 2. Here the slope was 1 over 1. So you went up 1 over 1, up 1 over 1, up 1 over 1. And those two lines intersected right there. That is our solution to this system of equations. That point is the point 1, 2, 3, 4, 5, 6, comma, -1. So if I plugged in the point 6, -1 into both of these equations, they should both be true because that point is on both lines. Well, let's check. 6, -1. -1 equals 1/2 of 6 minus 4. And -6 plus -1 equals -7. This side, the left side, is easy because yes, -6 plus -1 is -7. So yay us. That is definitely true. The right equation is a little bit uglier. 1/2 of 6 is 3. 3 minus 4 is -1. So that is also true. So we found the point that makes both equations true. 6, -1 is our answer. Okay, here is example B. So we have two equations again. We need to graph both of these equations. The first equation I'm going to do is this one because it is already in slope-intercept form. Y equals mx plus b, where this is the slope, and the b value, in this case it's the -1, is the y-intercept. So the y-intercept is -1. That's where the line crosses the y-axis, right here. And now I'm going to move the way the slope tells me to move. The slope tells me to go up 2 because this is positive. If that was a negative, I'd be going down 2. If this was -2/3, I'd go down 2 over 3. But it's not. It's positive. So instead of going down 2 over 3, I'm going to go up 2 over 3. Up 2 over 3. Up 2 over 3. And I'm out of space this way, so I'm going to continue the pattern in reverse down here. Down 2 over 3 the other way. Do you see how it still makes a nice straight line? It's in line with all the other ones. And I'm out of space. So that is my line. So that is the line y equals 2/3 x minus 1. It's good to label your lines so you know which line is which. It's not such a big deal with only 2, but there are problems later on. You might have a bunch of lines, and it's handier to have them labeled. All right, our second equation. The second equation, as before, this one is not solved for y. So we want to solve for y. We want to get the y variable by itself. That way it's in slope-intercept form, so we can graph it. So our goal here in this one is to start by solve for y. S-O-L-V-E. I don't know why it looks like a K. Solve for y. All right, so solve for y means get the y variable by itself. So this is being multiplied, so he's the last thing we get rid of. He's the first thing. Minus x, because he's positive. Big mistake I usually see here is people add x because they read this as y minus x. They read the paper going this way, and that's not true. It's not y minus x. This is a positive x, and it's a -3. So I have minus x on both sides. -3y equals -x plus 6. Divide both sides by -3. Y equals a little bit of ugliness. This division works out fine. This gives us -2. That's 6 divided by the -3. Now this -x divided by -3, that's not so pretty. Now we know the coefficient here in front of the x is 1. So this is a -1 divided by a -3. If we could make this prettier, it would be better. Then we can. We could just, a negative divided by a negative is positive. So this is just going to be 1 over 3. X. I take the number part here, and I pull it out as a fraction, 1/3, and then you just put the x after it. So this is 1/3 x, and then this division gave us this -2. So what we have here now is we have an equation solved for y, so it's in slope-intercept form. The intercept is -2. I'm going to do this equation in red. This is our y-intercept, so the line crosses the y-axis at -2. The slope is 1/3, so we're going to go up 1 over 3. Up 1 over 3. Up 1 over 3. Oh, that's getting farther away, it looks like. Up 1, 1, 2. Yeah, that's getting farther away. So if you look at it, it's going to cross down here somewhere. Down 1 over 3, and I'm out of space. Line, let's make it red this time. Start here, go this way. My points are not entirely accurate, but they're close. That point was a little high. There. Alright, so we have the intersection point now. It is whatever that point is right there. So that's the point -1, -2, -3, comma, -1, -2, -3. So the solution, we believe, is the point -3, -3. We're going to check it just to make sure we're right. We're pretty sure, but in the equation, I'll do them down here still. So we're going to check our work. If I plug in the point -3 for x, -3 for y, hopefully we get 6 here, and 2/3 of -3 minus 1. Okay. I guess we're just going to do the problem on the left first. So -3 times by -3 is a positive 9. -3 plus 9 is 6. So yes, that works for the first one. Check to see if that point is actually on the second line. So 2/3 times by -3 is going to be -2. You can check your math someplace else, or check my math someplace else, but it is -2. And then this math gives us -3, and yes. So I checked that point in both equations, and it showed me both equations are true. So that point works in both of them. We graphed our lines. We found the point of intersection. We checked our work. We're good. I would like you, please, to do the next one. This is letter C. Go ahead, pause the video right now. Do it on your own. When you're ready to continue, hit play, and we'll go through it together. All right. So, graphing. First equation is already in slope-intercept form. That is the y equals mx plus b, where again the slope, intercept. Slope, intercept. I guess I should include the plus as well. Intercept. So the intercept here is 4. So I'm going to, on my y-axis, put a dot at 4. 1, 2, 3, 4. And my slope is 1/2. Positive, so I go up 1 over 2. Up 1 over 2. Up 1 over 2. I'm out of space this way, so I'm going to do the reverse. Down 1 over 2 the other way. Down 1 over 2 the other way. Down 1 over 2 the other way. All my points form a nice, perfectly straight line. And there we go. That is the graph of the line y equals 1/2 x plus 4. My other equation, again, is not solved for y, so I'm going to go through the work of solving for y because that's the easiest method, usually. So subtract 2x because he's positive. Subtract 2x. Y equals a -2x plus 4. Okay. So this is now solved for y. That means -2 is the slope. Positive 4 is the y-intercept. So I'm going to put a point at positive 4 on the y-axis. 1, 2, 3, 4. Possible intersection point. Slope is -2. So because it's a -2, here, demo, the slope is -2. First off, we want the slope as a fraction. To turn any number, any whole number into a fraction, you put it over 1. And because the slope is negative, we're going to be going down 2 over 1. Down 2 over 1. So from this point down to over 1. We're going down because it's a negative slope, and negative slopes go down. Positive slopes go up. So positive slope going up, negative slope going down. And I'm out of space this way, so I do the reverse. Up 2 over 1 the other way, still in a straight line. Up 2 over 1, and there we go. Get ourselves a nice pretty red line going on here, and sweetness. Alright, so that point of intersection, what we thought was the intersection point right there at 0, 4, that's what he is, 0, 4, appears to be right. That appears to be on both lines. So the last thing we're going to do is we're going to check our answer just to make sure. We want to be 100% positive we have the right answer. So we're going to check it. If I plug in 0 for x and 4 for y, half of 0 plus 4, well, that's going to be easy because half of 0 is 0, and 0 plus 4 is just 4. So that one checks out. Other equation, 2 times 0 plus 4 equals 4. We get the same thing. 2 times 0 is 0. 0 plus 4 is 4. So that was the solution to both equations. Letter D. A football team managed to score 24 points using only safeties, which are worth 2 points each, and field goals, which are worth 3 points each. Together they scored 10 times. How many of each type of score did the football team get? So what I have for you is I have the verbal models written out for you just to give you the hints on what the two true statements are. So what I'd like you to do, I'd like you to come up with your equation. I'd like you to graph it. I'm not going to show you the next page because I think on the next page I have the equations written. I'm going to have you graph it. Try to do as much as you can by yourself. If you'd like to maybe write your equations and then stop and hit play and allow the video to catch up and so you can check to see if your equations are correct, that's fine. And then pause it and then try to graph it on your own before you watch me graph it. So go ahead, pause the video, do it on your own. When you're ready to continue, hit play, and we'll go through it together. Okay. So I have a verbal model written out for us. The number of total points is 24, so right there, 24 points. Points for safety. So again, I'm going to use the x and the y. So I'm just going to go ahead and assign the x variable to safeties, or the number of safeties, and the y variable to the number of field goals. Alright, so the amount of points they would get from the safeties would be 2 times the number of safeties they get, because every safety they get 2 points. So if they got 5 safeties, 5 times 2 would be 10 points. And the number of points from the field goals, since field goals are 3 points each, would be 3 times the number of field goals. So there's my first equation. Second equation comes from the second part of the problem. It says together they scored 10 times. So if with safeties and field goals they scored 10 times, it means the number of safeties plus the number of field goals together is 10. So those are the two equations that we should have come up with. So if you did not graph these yet, see, a little typo there, that should be a 4. If you did not graph these yet, go ahead, graph this now, find the solution, check your answer, then hit play, and we'll finish going through this together. Okay, so let's do our graphing. I'm going to use green. I haven't used green in a while. So I'm going to use this bottom equation here for green. First thing I need to do is I need to solve for y. Minus x on both sides gives me y equals negative x plus 10. And I remember that's a negative 1. As a fraction, because we want our slopes to be a fraction, it is 1 over 1. Alright, so I have my slope is negative 1 over 1. My intercept is positive 10. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the y-intercept. And the slope is negative 1 over 1. Because the slope is negative, I'm going to go down. Negative 1 over 1. Negative 1 over 1. Negative 1 over 1. And repeat, and repeat, and repeat. Doot, 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 doot. All right. So everywhere along that line is where this bottom equation is true. So if I scored, or they scored 10 times, they could have scored 10 of one and 0 of the other. They could have scored 9 field goals and 1 safety, or the other way around. All right. Our top equation, this 24 equals 2x plus 3y, in order to graph this again, it would be helpful if we had this in slope-intercept form. So I'm going to solve for y. Start by subtracting 2x on both sides. Gives me negative 2x plus 24 equals 3y. Divide by 3 on both sides, so 3's cancel. Y equals, this division is 8. This does not divide, so I'm going to leave this as a fraction, negative 2/3 x. And if it bugs you having the y on the right-hand side, we're going to take this whole equation, we could flip it, just so it looks more like we're used to seeing. So y equals negative 2/3 x plus 8. There's absolutely nothing wrong with doing that. So now we have our slope here and our intercept there. So the intercept is 8 right there. And the slope is negative 2/3. So negative 2 over 3. Down 2 over 3. Down 2 over 3. Down 2 over 3. Down 2 over 3. I'm going to draw myself a pretty little line in there. Isn't he pretty? All right. And as we're doing our graphing, I think I found the intersection point right there. That's where both situations would be true, where the total number of points they scored is, or the total number of times they scored is 10, and where they scored a total of 24 points. And so I'm just going to check the equation. I'm going to erase all this stuff over here. And that is the point. Let's see, 1, 2, 3, 4, 5, 6, comma, 1, 2, 3, 4. So if I check the point 6, 4, it hopefully is true for both of them. So the top equation, or I'm sorry, this one, bottom one, 6 for x, 4 for y equals 10, and yep, better believe it, 10 equals 10. So that one's easy. The other one, 24 equals 2 times 6 plus 3 times 4. Right, so let's see, that's 2 times 6 is 12, and 3 times 4 is 12, giving us a total of 24 points. It checks out. So that point is true for both equations. It is the solution to this system of equations. Okay, so for our summary here, we have a type 2, and it says, if you have a graph of 2 linear systems, how do you find the solution to the system? Should be pretty easy if you pay attention to the lesson. So go ahead, answer that in your summary. And this is a type 2, so make sure you get it correct. This has been lesson 4.11. Thanks for watching.